Hello friends, this video on DNF block elements part 24 is brought to you by examfear.com. No more fear from exam. Let's talk about the complex ions. These complex compounds are actually formed when the metal ions, typically in this case my transition metals, they bind with numbers of anions or neutral molecules, right? And they bind to form a complex species. And this complex species has some characteristics. This one, if you see, is hexa aqua copper. One copper with 6 water molecules. Okay. Another example of complex ions can be FeCN6 3- or FeCN6 4- or CuNH3 4 2+. So here this NH3 Cn-, these are all ligands. Okay, and these transition metals actually form large number of complex compounds. Why? The reason is why large number of compounds. The first reason is size. Size is small for the transition metal. Size is small. Next is the ionic charge is high. Ionic charge is high for transition metal. Okay, and third is the d orbital electrons. D orbital electrons are there, so we have s and d orbitals electron, more electrons for bonding. Okay, and these d orbitals electron actually accept the lone pair of other group. So even if it has vacant d orbital, it is useful. Even if it has some electrons, it is useful, right? It accepts the electrons donated by the group. Okay, and these ions with such characteristics having strong tendency to interact with ligands such as water, ammonia, Cn-, all of which have highly electronegative atom and unshared, etc. Okay, see what I'm saying is these ions, these metal ions, for example metal ions, these metal ions have tendency to interact with these ligands. Ligands, for example, my ammonia, Cn-, water molecules. So these ions have tendency to attract, form bond with these ligands. Okay, and these ligands actually have highly electronegative atom. For example, if you see nitrogen, oxygen, these are all highly electronegative atom, and these have unshared electron pairs also. If you find actually draw the shape, you'll see that they have unshared electron pairs. Okay, these metals with positive charge or metal ions interact with ligands. These ligands are ammonia, Cn-, water molecule, and these ligands have the highly electronegative atom and unpaired electron, and these bind together and they form complex ions. Okay, now the next important part of the D block element is the catalytic properties. See, what are catalysts? Catalysts are nothing but any substance which accelerates the rate of reaction. For example, this is a biological catalyst. This catalyst, the grey one is my catalyst. This catalyst provides a site where the reaction can happen. It forms an intermediate complex, and with this, the product is easily formed. This was my reactant, and you get product using this catalyst because this catalyst is not being used, but it helps in providing the space surface where the reaction can happen. And also sometimes the intermediate complex is formed, it's easy to break. Okay, now the transition metals, I am saying they have catalytic property. Why? See, there are several reasons. The first is the transition metals have ability to adapt to variable oxidation state. This variable oxidation state is one of the key reasons. We'll discuss these in details now. Okay, second one, it forms complex, you just seen, and these complex you can also form unstable intermediate complex. The way we have seen this unstable intermediate complex, it forms. The third is it has partially d-filled orbital, partially filled d orbital, and this d orbital actually this provides active site. This provides active site and also the large surface area for adsorption, or I can say Adsorption. Adsorption of what? Adsorption of reactant molecules. And that's why if you see the in hydrogenation we use platinum, but we make sure this platinum is very minute. I mean very crushed. It's crushed so that, or it's powdered so that you have more surface area. You have anything, you crush it, you make it powder, effectively you end up increasing the surface area. Right? So this has this property. Because of these three properties, actually these d block elements have catalytic property. Okay. Let's see the examples of this. For example, the first one, the variable oxidation state. If you see Fe3 plus, this has capability of converting it to Fe2 plus easily, and this catalyzes the reaction between iodide and persulfate. We'll show you. For example, you take Fe3 plus, you react with I minus. What you get is this. The iron is reduced, variable oxidation state, and this reduced iron actually react with persulfate and gives back Fe3 plus, and you get SO4 minus. So now if you see, you started with Fe3 plus, you get back Fe3 plus. Thus Fe3 plus is nothing but a catalyst. But because Fe3 plus could actually change its oxidation state easily, it acted as a catalyst. If we talk about these two, complex, unstable, intermediate, and it gives active site. So a good example is iron. Iron is actually finely divided iron is used as catalyst for manufacturing ammonia. For production in Haber's process. In Haber's process, we use finely divided actually. Finely divided. Why finely divided? Because if you finely divide any metal, you increase the surface area, and we want more and more surface area where reactant can be adsorbed and the reaction can take place. Another again, the nickel powder. Nickel, this is also in powder form, is used as a catalyst in hydrogenation of unsaturated hydrocarbon. We have seen that. Platinum again, the finely divided platinum is used as catalyst to manufacture nitric acid by Ostwald process. This Ostwald process, we produce nitric acid, and that we use platinum as catalyst. There are so many examples. V2O5, vanadium pentoxide. This is also used to manufacture sulfuric acid, where vanadium pentoxide is my catalyst. Okay. So as I told that these provide surface area, these catalysts, because this catalyst now has the d orbital and s orbital. So these d and s orbital electrons, actually it helps in binding the reactant to this surface area, and with this the concentration of reactant in the surface area increase. Since the concentration is increased now at some some local place. For example, this is my catalyst. At this, if I increase the concentration of reactant, why? Because this reactant forms bond with this d orbital. Since the reaction of the concentration of the reactant has increased in this area, the reaction is faster. Okay. So that's the role of catalyst. This was the picture for the hydrogenation. If you see, this is hydrogen, this is a nickel catalyst. This is the nickel catalyst, and hydrogen bonds are broken, and this nickel provides a surface area where this reaction can take place and hydrogenation take place. So if you want more details on hydrogen, you can watch my videos where we have discussed the process of hydrogenation in more detailed way. Now we'll talk. Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again. For the trend